Welcome back to the video series on integration and differential equations. Today we're going to see a second method for solving DEs. The type of DEs that we're going to be working with today are called first order linear DEs, or sometimes just linear DEs for short. Here's our example. We're going to find an explicit solution, meaning we're going to solve for y. We're given a differential equation as well as an initial condition. We're going to run through the 6-step procedure for solving linear DEs. First step, we're going to write the DE in standard form. And standard form for a linear DE looks like this. The first term is just a dy, must have a coefficient of 1. Second term, we've got p of x, y dx. P of x here can represent any function of x. It could be a constant. The only thing it can involve is a y. So you couldn't see something like sine y here. That would not be allowed. But any function of x or any number is fine. And then over on the right side, q of x dx. And again, q of x here, that can be a function of x, like say e to the x or sine x. It could be a number as well. Okay, so let's see if we can put our DE, which is right here, let's see if we can put that in standard form. So what would have to happen is that term with the y dx in it, this term here, that would have to come over to the left side. We'd write dy minus 7y dx is equal to e to the 4x dx. So negative 7 is playing the role of p of x, and e to the 4x is playing the role of q of x. So yes, that's in the standard form. And after you do a few examples, you get used to what standard form should look like. So there we go, that's our standard form. Step 2, we're going to calculate e to the integral of p of x with respect to x. And this expression that we're going to calculate, it's called the integrating factor, or sometimes we'll just call it IF for short. It's good to give it a name because we'll be referring to it later on in the problem. So first step here would be to figure out what function is playing the role of p of x. So let's look back at our standard form. P of x is just the name that we give for the function that's multiplied by the y dx. So in our version of the standard form here, what was y dx multiplied by? It was multiplied by negative 7. And it's important that if this term is negative, that we're actually bringing that negative into p of x. So p of x here, negative 7. So let's integrate p of x with respect to x. That would give us negative 7x plus a constant. Now, in fact, we're going to omit the constant at this point. And this is something that we'll always do when we're solving these linear DEs. So in step 2, when we're calculating this integrating factor, we omit the constant. There will be a constant of integration later on in the problem, but in step 2, we always omit the constant. All right, so now to get our integrating factor, let's write IF is equal to, it is e to the integral of p of x. And now that we've done that integral, we know the correct exponent to put on here is negative 7x. So e to the negative 7x is our integrating factor. Step 3, we're going to multiply the standard form by the integrating factor. So we're essentially just putting our first two steps together. In step 1, we got our standard form, so I'll put a box around that for clarity. That's our standard form, and we're going to multiply that by the integrating factor that we just calculated, which was e to the negative 7x. All right, so let's multiply through. We'd have e to the negative 7x times dy minus 7 times e to the negative 7x times y dx equals e to the negative 7x times e to the 4x dx. Okay, so we have indeed multiplied each and every term. All three terms have been multiplied through by the exponential. The only other thing I would point out here is we could do some simplification on the right side. Multiplying those exponentials, the exponents are going to add, so we'd have e to the negative 3x dx would be just a simpler way of writing that right-hand side. Okay, so that's step 3 done, and we are halfway through the problem. All right, I'm keeping the problem on here, the original statement of the problem, in case we want to refer back to it later, and we're moving on to step 4. Step 4, we're going to create a differential, and then we will integrate. So for this step, it's really helpful if you watch the previous video on the product rule for differentials. If you haven't watched that video, I suggest you go back and watch that now, because we're going to use that process, use that discussion that we had in this process of creating a differential. All right, so here was our previous step. And what we want to do is express the left side here as a single differential. Okay, so we saw the shortcut for doing that in the previous video. We're going to find the dy term. We're going to replace the dy with a y, so that would give us e to the negative 7xy, and that expression is going inside the differential. So we believe that this differential here, or at least hopefully you believe, that this differential here, this expression here, is exactly the same thing as these two terms. So let's convince ourselves of that just by applying the product rule. If we applied the product rule to this differential here, we'd have e to the negative 7x dy, so that's our first term, and then plus y times the differential of the exponential. So that would give us y times negative 7 e to the negative 7x times dx. So yes, this little differential here is the exact same thing as these two terms. So we've managed to rewrite that left side in a much more concise way. Okay, so I'll just recopy the right side here. No change happening there. Okay, now at this point, I'm going to put a big happy face. We've created a situation where it is now super easy, or at least fairly easy, to integrate both sides of this equation. So let's integrate both sides. We're going to integrate the differential of e to the negative 7x times y, and that's going to be equal to the integral of the right side. Okay, before we write down our integrals, let's just have a little refresher here. Maybe I'll do a refresher up here. If we integrated, say, dw, I'm just coming up with a random name for a variable. Let's say w is the name of our variable. If we integrate dw, that's 1 times dw. We get w plus a constant. This is similar to how if you integrate dx, you get x plus a constant. If you integrate dy, you get y plus a constant. Well, what we're really doing on the left-hand side here is we're integrating differential where our variable is called something a little bit complicated. Our variable is called e to the negative 7x times y. But nonetheless, we're just integrating a differential. So it's similar to how when you integrate dw, you get w plus a constant. If you integrate d blah, whatever your blah is, you're going to get blah plus a constant. So what's going to happen is we're just going to get e to the negative 7xy plus a constant. That's why we worked so hard to describe this left-hand side here as a single differential, because differentials, super easy to integrate. All right, so with that in mind, let's integrate both sides of this equation. So on the left side, The integral just gets rid of the differential and we get e to the negative 7x times y. On the right side, we're doing our usual sort of integration. We've got an exponential here, so e to the negative 3x divided by negative 3. So I'm going to say minus 1/3 e to the negative 3x plus c1. Just a reminder here about constants. Remember that when we're solving differential equations, when we're integrating both sides here, we only need one constant of integration. We just place that constant over on the right side. It would be redundant or overkill to have C1 on the left side, C2 on the right side. So we just need that one constant. I'm just going to call it C1 only because we used C in this little discussion that we had up here, but really C or C1 would be a fine choice at this point for the name of your constant. So that is the calculus part of the problem done. We've got 2 more steps to go, but they're both algebra steps. So step 5, we are going to solve for y. Remember that we want an explicit solution at the end of the problem, so we want to have y equals something or other as our final answer. So here's our most recent equation here. If we want to isolate y, you could think of it as dividing by this exponential here. But what I find a little bit more convenient is to think about it as multiply by e to the positive 7x. So if we multiply by e to the positive 7x, that's going to create a 1 as the coefficient for the y, and that will be a little bit simpler to deal with on the right side here. So multiplying through by e to the 7x, we'll have y equals minus 1/3 e to the 4x plus c1 e to the 7x. Okay, I feel like I went through the algebra a bit quickly, so I'm just going to move that step down here. I'll show a bit more work. So as we multiply through by e to the 7x, the exponentials on the left will cancel. On the right, we get minus 1/3 e to the 7x times e to the minus 3x plus c1 e to the 7x. And in that second term there, the exponents will be adding because we're multiplying. So that's how we're getting that minus 1/3 e to the 4x in that second term. Great, so we are almost done. We've now got an explicit solution. The very last thing we need to do is just use our initial condition. So step 6, initial condition if applicable. Some questions don't come with initial conditions, in which case you ignore this final step here. Alright, so our initial condition is that y of 0 equals 2, meaning if we plug in the x value 0 and the y value 2, we're going to be able to solve for our unknown constant. So let's look back at this step here and let's plug in. So we'd have 2 equals minus 1/3 times, well, e to the 0 is going to be 1. So I don't really even want to write that down. I just want to say 2 equals minus 1/3 plus this unknown c1 times, and again, e to the 0 is going to be 1. So I don't really want to write that 1 down. I just want to say plus c1. Okay, so there we go. Let's solve for c1. We'd have 2 plus 1/3 is equal to c1. So in other words, c1 is 7/3. Now that we know that, we're going to take that information, plug it back into our most recent version of y, and we'll have our final answer. So y equals minus 1/3 e to the 4x plus 7/3 e to the 7x. Let's put a box around that, because that is our final answer. So that is an explicit solution. We have solved for y, we have used the initial condition, and that is a function which solves the original differential equation.